Next gas law that we're going to cover is Boyle's law, problems 1 through 3. So this is the formula for Boyle's law that we will use in class. This is a generic formula. When we go through Boyle's, Charles, and Gay-Lussac, you're going to see that one of the three conditions of pressure, volume, or temperature are held constant, meaning it does not change. So in this case, I have no temperature, no T, so therefore temperature is held constant with Boyle's law. So we have P1 V1 equals P2 V2. That means we're going to see a change in pressure and in volume. Okay, number 1 says a gas occupies 12.3 liters at a pressure of 400 millimeters of mercury. What is the volume when the pressure is increased to 600 millimeters of mercury? So I see a increase in pressure, and we are going to look to see how that affects volume. Volume and pressure are inversely related, which means we should see them do opposite things. So pressure is increasing in this case, so we should see volume decrease. So I was careful to do some coloring arrangements for you. We know that liters measures volume. We know millimeters of mercury measures pressure. These two are both ones because they occur at the same instant, meaning they occur at the same conditions. I know that when this pressure is this, it's this volume, or when it's this volume, it's this pressure, according to the way this word problem is read. And then we're looking for a volume later when the pressure changes to this. So we put our generic formula, P1 V1 equals P2 V2. We plug numbers in, 60 millimeters of mercury, 12.3 liters equals 600 millimeters of mercury times V2 are unknown. We make sure whatever we have two of, in this case pressure, they are the same unit, which they are, which means that I can divide, think of the math here, we're multiplying, and multiplying times x, which are unknown, so we're going to multiply the left, divide by the number on the right. When I do that, millimeters of mercury units would cancel, because I'll have 40 millimeters of mercury divided by 60 millimeters of mercury on both sides, and then millimeters of mercury would cancel, leaving me just liters on this side as a unit, and I get 8.2 liters. Example number 2. So here it says if a gas at 25 degrees Celsius, that's a temperature, occupies 3.6 liters, that's a volume, at a pressure of 1 atmosphere. So all of these are happening at the same condition or same moment. So they all get a subscript 1 in this case. What will the volume what will it be its volume at a pressure of 2.50 atmospheres? So I want to know what its volume is when its pressure changes. Notice temperature has no change, so as we know in Boyle's law, temperature remains constant. Because we see no change in temperature, or we're not asked or given temperature, a second one, we know that we're still in Boyle's law. P1 V1 equals P2 V2. I'm going to plug in 1 atmospheres for P1, 3.60 liters for V1, 2.50 atmospheres for P2, and then V2 is my unknown. Multiply the left. Before we do that, let's talk about the fact that we have 2 units of pressure. They're in the same unit of atmosphere, so I can do that, use them in the math. If they weren't, I would convert one to the other. So I'm going to take 1.00 times 3.60 liters, divide by 250 liters. Atmosphere units will cancel, leaving me units of liters only, and mathematically, I will get 1.44 liters. Example 3. To what pressure must a gas be compressed in order to get it into a 3 cubic feet tank, the entire weight of the gas that occupies 400 cubic feet at standard pressure? So the term standard pressure means pick a pressure. In this case, it wants an ATM. So one of the standards that I showed you in the beginning of this video, you're going to pick one of those, and you're going to pick ATM in this case. So this is the way this problem is worded. You have to be able to understand that this volume goes with this pressure. So I made them both ones because of the way the problem is worded, because it says to what pressure, so that indicates a later pressure or a second pressure. So because these occur at the same moment, or are the same conditions of the gas at that moment, I made them both ones, and I made this my P2, and this pressure goes with this, because I'm trying to get what the pressure is when it's this volume. So this is my V2. Cubic feet is a volume. Feet times foot, or foot times foot times foot would be cubic feet. So P1 V1 equals P2 V2. I have 1 ATM and 400 cubic feet, so I'm just plugging my givens in from my word problem that I labeled carefully. Then I plug in 3 cubic feet, and I see that I have 2 units of volume, 2 volumes, and they're both the same unit, so I can use them mathematically. Multiply the left, divide by 300. When I divide 300 cubic feet over, mathematically I get 1.33 ATM because cubic feet cancel. Okay, one last thing I want to go over. If you remember when I first started talking about number 1, I said that pressure and volume are inversely related. As one goes up, the other goes down, or as one goes down, the other goes up. So let's look here. We saw pressure going from 40 to 60, so it went up, and look, volume went from 12 to 8. So that follows the rules that we would expect. Example number 2, we saw pressure go from 1 to 2.5, so it went up, so we should see a decrease in volume. We see that here. And then example 3, a little trickier to think about because it's kind of backwards, but we know that what we have 2 of is volume, and volume went from 400 down to 3, from 400 down to 3, so we should see an increase in pressure, and pressure went from 1.00 atm standard to 133 atm, so it increased. So they, in fact, all 3 represent an inverse relationship.